This is Professor Jeff Wilkerson at Luther College, bringing you an introduction to Project 3 from Astronomers as Observers and Experimenters, published by Kendall Hunt. This is one of my favorite projects in the book. Well, there's 3 projects in the book, so you know. This is one of my favorite activities in the entirety of the book. And we've been doing something like this project in one form or another in the course that I teach every fall for a number of years now. And it's a way for us to bring together many of the ideas and many of the skills that we've developed over the course of the semester into one culminating project. And the way we've done it is we have taken typically a week off of lab. And so one lab week is devoted to this project in addition to the work the students do outside of class. And it can be as significant, it can be as detailed as you would like it to be, or you can really pare this back. If you're thinking about undertaking this exercise, this project, and you haven't looked at exercise 25, I think that's the right number now, the color magnitude diagrams of open star clusters, it's really worth taking a look at that, because we're building on the ideas from that exercise to say we're going to start what we did there and expand this out and see what we can learn. And what we learned in that exercise, exercise 25, is that there is the intrinsic colors of stars, the color indices, B minus V, is what we'll use in this project. The intrinsic colors of stars, which we call B minus V naught in that exercise, is different from the measured color index. And we ask you at the end of that exercise, how the heck do you know? How can you go about finding, if you measure something, how do you know what the intrinsic value is? And so you remember that the color index is a measure of the temperature. So if you have another way into the temperature that doesn't depend on the scattering that's going on, then that's a way that you might be able to get to the intrinsic color of the star. And in this case, what we're looking at there is really, that's the idea. The light from stars is reddened as it comes to us because it's passing through matter in the galaxy. And as it passes through matter in the galaxy, the blue light is preferentially scattered out. If it's passing through dust, it goes as 1 over lambda cubed, more or less, and it goes 1 over the wavelength cubed, and it goes as 1 over the wavelength if it's dust grains, typically. And so, but in any event, the shorter wavelength light gets scattered more than the longer wavelength light. And so you want to look at that and say, okay, what we looked at in that exercise is to say there was a distance dependence. We overestimated the distance to stars is what we looked at there, star clusters, because in addition to making them redder, it makes them look fainter too. So we have all kinds of challenges going on due to the material in the galaxy that the light is coming to us through. And we have to try to overcome those challenges in order to understand what we want to understand about the stars and star clusters in exercise 25. We're flipping that in this activity, in this project. We're saying, okay, let's use that to our advantage and see if we can map the stuff in the galaxy. Can we look to see how reddening depends on direction we look in the galaxy and depends on the distance into the galaxy and all of these things? Can we start to get a handle on the dust and gas that's in there? Complications abound. And that's what makes this such a great project, is you can think about how to refine this any way you want. There are some suggestions in what we wrote into the text that say, here are some ways you might want to think about refining your analysis, but it's your project and you should go after it. We don't want to give you too many tips. We want you to think about this the way you want to think about this and do this the way you want to do this. And so, for example, you go to WebDA site. So there's this is a web version of the BDA catalog. It's a good old catalog of star data. So you're going to WebDA, and when you're there, you're going to look up clusters, and we recommend in the write-up looking up as a function of right ascension, hours of right ascension, and to say I'm going to look at a certain direction in right ascension because that maps what we're doing from Earth. We're looking this direction through the galaxy. You could instead look at galactic longitude, which measures actual position in the galaxy. And that might be a more interesting way to cut your galaxies if you wanted to say, I'm going to look along this slice of longitude, which is to say, okay, let's let's draw a galaxy, not necessarily our galaxy, but a galaxy, and suppose that we were here. And if you were looking at longitude, you'd be looking along one particular direction like this, or something along there. But if you're looking in right ascension, it's centered on us. And so you're looking out this way, or you're looking out this way, or you're looking this way. Okay? And so that's what you're trying to do is to see how the reddening depends on, say, distance in this direction. And it's also possible that some of the reddening is intrinsic to the star clusters themselves. Star clusters are born out of clouds of gas and dust. And so there's gas and dust. Some of these may be dustier and gassier than others. And we have a model that suggests that maybe younger ones haven't cleared out all of that material as efficiently. And so they might have a little bit more reddening than older ones. So it would be maybe worth your while to investigate these as a function of reddening, as a function of age of the clusters, and maybe eliminate clusters if it looks like there's a dependence. So you can start to cut clusters out. You can say, I'm not going to use this cluster in my analysis. Suppose I'm looking this direction through space, and I want to know what the reddening looks like as a function of a distance through the space, and I'm going to use that as a measure of what the dust and gas, the material in the galaxy, looks like as a function of distance through the galaxy that direction. But what I found is very young clusters have a lot of reddening, or the reddening is noisy. So if I look at a bunch of clusters, so one thing you might do is slice in distance. So look in distance at the WebDA site, get the distances of your clusters, and pick a narrow range of distances. And so all your clusters are in the same direction, and they're all the same distance, more or less. You can't slice it infinitely thinly, but they're all the same distance in the same direction. And then you can say if there's a range of ages in there, does having factored out direction and distance, does age seem to make a difference? And if it does, is there a range of noisy ages? You might need to do this 3 or 4 or 5 times in different directions. And as you do this 3 or 4 or 5 times in different directions, you might find out, oh, younger clusters aren't uniformly redder than reddened more than older clusters, but there's more scattering in their reddening, and we're still better off eliminating them. Or maybe you need to eliminate very old clusters, and you want to slice middle-aged clusters and only use middle-aged clusters. Now, you also might want to slice things that aren't in that. We talk about this in the write-up, I'm sure. You might want to slice out things, eliminate things that aren't flat in the plane of the galaxy. So look at galactic latitude, where things are up and down in the galaxy, and say if they're way out of the plane, we're not actually looking through the plane of the galaxy anymore, right? And so maybe we want to eliminate those too. We also recommended in there you eliminate the ones that have a lot of data missing. It just means we haven't studied them very much. We don't know as much about those clusters. So if most of the data columns are empty, when you look up the data files on WebDA, just walk away from those is my recommendation. But it's your project, and you might want those to get the data that you need. Understanding that they're probably a little bit noisier, we probably understand those clusters less than other clusters. So that's the idea here, is to say maybe you start by doing a cut on ages and see if you want to slice on ages. Now we also have directions. Maybe you want 1 hour of right ascension or 2 hours of right ascension. An hour of right ascension is actually a pretty broad angle that you're looking through space, and as you get further out, it's a pretty big cone. You're looking through a lot of space, and you'd actually prefer, instead of looking in a full hour of right ascension, you'd prefer to look in half an hour of right ascension, or 15 minutes of right ascension, or 5 minutes of right ascension, or something along those lines. A narrower and narrower slice of right ascension is going to narrow this direction down, right? If you're looking through a full hour of right ascension, this thing gets to be pretty broad by the time you get out there, right? Or 2 hours of right ascension. But if you're not looking through that much right ascension, you don't have enough clusters to do the job that you want to do. And this gets right to the heart of a problem that will always follow you when you try to do an astronomical project like this. This is one way observing in astronomy is fundamentally different than experimenting in the lab. When I do an experiment in the lab, I can, in theory, in most instances, just run longer. I can set up and redo the experiment and run and run and run. We have so many open star clusters. We have so many stars. We can see so much in the galaxy, and that's it. We can't build more stars. We can't build more star clusters. We can't do more, and so we're kind of limited. And so we want to look in as narrow a range of right ascensions as we can, but got to have enough star clusters to do this. And so this is one of the tricks. This is you work your magic as you're doing this project and figure out what the best way to do this is, especially if you've sliced out old clusters and young clusters, and you're only using middle-aged clusters, and you're looking in a narrow region of space, a narrow slice of space. You may have very few clusters, but you may get a very clean relationship. So you may want to do this project a few different ways. You may want to do it with a broad range of right ascensions, so you get a lot of clusters, and with a broad range of ages, so you get a lot of clusters, and see what it looks like with a lot of clusters in there. Or you might want to tighten those things down and see what it looks like when you tighten those down and try to get the noise out of there. And try this several different ways and compare the results you get each way. Now, if the dust is uniformly and the gas is uniformly distributed through space, then you would expect the stars to get uniformly redder as they get more distance. And you might make a graph of color excess. That's this measure of observed color index minus intrinsic color index. You might make this color excess as a function of distance. If it's uniform, it might look something like this. I'm not arguing that it's a line necessarily. That's for you to figure out and to think about, or a curve like this or something like this. But it's a smooth step up. Now, if it's clumped in space, it might be a smooth distribution. Then you hit a dense cloud of stuff. And then when you do that, you're walking along, and you suddenly jump up because you hit a dense cloud right there. Boom. In front of that cloud, there's one reddening, and behind that cloud there's another reddening. Or there may not be much stuff in space at all. There might only be clouds. So it might be basically no reddening, jump up, no reddening, jump up. You see how you hit a cloud, you jump up. You hit a cloud, you jump up. Everything on the other side of that cloud is reddened. And so you might be able, this is the kind of thing we're trying to get at. What can we do? Now, if we have spiral arms like this, you might expect something like one of these to say you're looking through stuff. Boom, you hit a spiral arm, you get a lot of stuff. And then you're between spiral arms, boom, you hit a spiral arm, you get a lot of stuff. And so you can imagine something like this, just due to the nature of the spiral arms of the galaxy. Or within a spiral arm of the galaxy, you're going to have clumped matter. You're going to have clumps of dust and gas, and you're going to hit those as well. So you might expect that even within an arm of the galaxy. Within an arm, if you're looking between arms and you hit an arm, you might expect it to look more like this. If you're looking down an arm, you might expect it to look more like this. I don't know. And again, it depends on how good a job you can do of narrowing your line of sight so you're actually looking down that thing. And it may not be possible to do a good job with this at all, but this is a way you start. So we're going to say, this is the question we want to answer. All good astronomy projects tend to start with a question you want to answer. How are the dust and gas distributed in the galaxy? And then we say, well, is this technique a good enough technique to measure this? Don't know, but we don't know till we try. We can make some guesses maybe, but we don't know until we go out and we actually try to do this, whether we have any hope of making this work or not, or whether we need to refine this, or whether we need to toss it out. As with the other projects, that's what you can do with this project. You can say, yeah, we can do what we want to do, or we can't do what we want to do, but it hints at how we might be able to do a better job, or this technique is never going to work for us to be able to do the mapping that we want to do. And that's the life of the astronomer. That's the idea. Have an idea. Go and start to take the data and work on that idea and see what you find out. Now, in order to see how this looks, I would recommend that you look at several different directions in the galaxy. You might expect that it's just dustier toward the center of the galaxy than it is toward the anti-center of the galaxy, or 90 degrees away from the center of the galaxy. Might look different from either one of those, but again, it has to do with where our spiral arms are, maybe. So remember, it's more complex than just that. But the idea is, if you look this direction in the galaxy, and this direction in the galaxy, and this direction in the galaxy, and this direction in the galaxy, you'll probably see different things. You'll probably have evidence that if one of those regions has a uniform dust and gas, and it's a lot of dust and gas, you might get a very steep line or curve, and another direction might have a very shallow curve like that. And so there's all sorts of questions you can start to answer. Go through it once, probably answer as many questions as you can, and then refine the technique and see if you get a different result, and see if it helps you understand if you narrow down the direction you're looking, or you cut out ages of clusters or something like that. What happens if you if you pinch this thing down, and is that a good thing or is that a bad thing, and what's going on? So that's really what we got, is to say this is trying to take some of the stuff that we've used elsewhere in the textbook and pull it all together to see if we can build some sort of map of what's going on in our galaxy. It's a daunting, and probably we're not going to get results that we love, but getting results that are confusing and maybe hint at something, they give us a path forward. And so that's what we're trying, that's the best we're trying to do here, is to get a project to say, will this work? Here's an idea. Will this work? You may have your own idea of something you want to measure, and some catalog you want to go to get the data to measure, and great, to go do it. That's what we want, right? We've become astronomers. We've really bought into this idea of us being part of this astronomical enterprise. If that's where we are, if we're at the point where we say, yeah, let's go get this thing. I have an idea of what I want to measure. I don't know if this technique is going to work or not, but I'm going to develop a technique and I'm going to try it. I'm going to see what I can learn from it. And so think about this project in that way and see what you can learn about the dust and the gas in the galaxy, if anything, and learn about the technique, if anything, to do this, and refine the technique as you will. Please don't hesitate to contact me if you have any questions about it. I hope you find this interesting, fun work, and I hope you enjoy doing this, and I hope you learn something interesting. And it's a great project to do with other people, is to say, we're each going to take a slice, a direction in the galaxy, and then we're going to compare our notes. We're going to get together at the end and say, here, this group did look this direction, this group looked this direction, this group looks like this way, this way, this way, this way, this way, and to see if we can start to get some sort of larger map of what's going on by pooling the data that everybody took and thinking about this as a big group project, not just a single person's project. So anyway, however you go about it, good luck with it, and we'll have more for you at some other time.